let us now look at what happens to the gases that are flowing downstream of the combustion wave if the wave happens to be a deflagration wave or a detonation wave. What we have seen so far is if you have a deflagration wave, it is an expansion wave, and so you have the reactants react into products, and the product gases downstream of the wave will have the pressure decrease a little bit and density decrease, and they would get accelerated. And if the acceleration is just only mild, then the deflagration wave of course propagates at a subsonic speed relative to still reactants, and the products will also be accelerating only up to subsonic speeds. But if it is a Chapman-Jouguet deflagration, it can get accelerated all the way up to sonic velocity, or if it is a strong deflagration, it can get accelerated all the way up to supersonic velocities, which of course we have been saying is forbidden by the second law. On the other hand, if you now look at the upper branch of the Hugoniot curve, we have a detonation wave that propagates at supersonic speeds relative to still reactants, and the products go through a compression, and that means they are having a pressure rise and a density rise, and then they get decelerated, and for a weak detonation they do not get decelerated significantly, so the product velocities still turn out to be supersonic, whereas for Chapman-Jouguet detonation it is turning out to be sonic, and for strong detonation it gets decelerated all the way down to subsonic speeds. This is what we have noticed. What we want to now look at is what is the direction of this velocity of the downstream gases. What does that mean, right? So we have this wave that we wanted to keep, and then we have been thinking about a wave fixed coordinate system in which the wave is like this, and then the gases are coming in, the reactants are coming in, and the products are moving. So we thought the directions are all fixed, right? Alright, but then keep in mind that if you now allow for a lab fixed coordinate system in which you have still reactants and then you want to have the wave move, right, that means you want to now subtract out the incoming velocity from the entire flow field and now start looking at whether the reactants are going to still be going like this or going like this. In other words, sorry, products. So the reactants are still and the wave is moving, and we now subtract the reactant velocity from the product velocity as well, and then we want to find out whether the products are going to be going like this or going like that, or still in other words we want to know whether the products are going to actually follow the wave or go away from the wave, right. So that's what we want to do now, and let us see how to do this. So downstream velocity at non-CJ points, whatever we do actually also applies to see the CJ points as well. It is just that when we say non-CJ points it is a lot more general when compared to what we have done before, which is to look at the Mach number, downstream Mach number at the CJ points, from where we just generalize saying that weak detonations will have supersonic downstream velocities, strong detonations will have subsonic downstream velocities, and so forth, by just noting that the CJ detonation or deflagration will have sonic downstream Mach numbers. But here what we are trying to do is to determine the direction of this velocity relative to the wave for any point, not just the CJ point. So this is applicable to non-CJ points as well. So let us now look at the detonation branch. So in the detonation branch, so in the detonation branch of the Hugoniot curve, right, we have 1 over rho infinity is less than 1 over rho naught, right. Therefore, we have u infinity minus u naught equals m dot times 1 over rho infinity minus 1 over rho naught. You know how to get this, which is less than 0, which implies that u infinity is less than u naught. This is no news. We know that the downstream velocity is going to be less than the upstream velocity because the flow is getting decelerated, but that is in a lab fixed a flame fixed coordinate system or a wave fixed coordinate system. So if you now have a wave that is fixed in a coordinate system and you had a u naught like this and u infinity like this is what is the story, right. But if you now look at so this is wave fixed, right. But if you now have something like a lab fixed coordinate system where you're saying let's now have the wave move with the velocity v wave, okay, and we now suppose that your reactant velocity is in this coordinate system designated as v naught, and let's say it's set to 0. That means we are having still reactance, right. And in our notation, let's now say that we want to have our v infinity follow the wave, right. That is simply saying I want to subtract u naught from this, and if I were to now subtract u naught from here, it's going to become 0. That's what I'm going to get here. If I now subtract u naught from here, the question is the arrow going to flip or not, okay, is it going to continue to be this way or not, okay. That means we want to basically find out whether v infinity minus u naught is going to be positive or negative. That's exactly what we are looking for, okay, assuming though that this v infinity is going to be in this direction. So let us now do the coordinate transformation. So v naught is equal to v wave minus u naught, and v infinity equals v wave minus u infinity, right. So essentially now the v wave is now thrown upon this picture. Therefore whatever we are actually now beginning to see here for the velocity is going to be v wave subtracted velocities. Therefore now if you have still reactance, so this is the lab fixed coordinate system, for still reactance right, v naught equal to 0. So just in case you have been wondering how come we have a v naught, yes, we will now try to set it to 0 to indicate that we have still reactance, which means that our v wave is equal to u naught. Now notice this carefully, we can say v wave is equal to u naught because of the way the arrows are marked. If you now take your arrow for the v wave to be rightward, that is when it is equal to u naught, with the u naught actually marked this way, alright. That is basically say that the v wave exactly opposes u naught in the wave fixed coordinate system, therefore your v wave is becoming stationary, right. So this is having the directions taken for these two things embedded in it when you now say v wave is equal to u naught, alright. If you now say that, then v infinity we can now plug V infinity is taking the direction of V infinity to be following the wave. If you now do that, then V wave can be substituted as u naught, and you can now get u naught minus u infinity, right. But what did we notice for u naught minus u infinity? U naught is greater than u infinity, which is now greater than 0, right. So u naught minus u infinity is greater than 0. So if you now have u naught minus u infinity greater than 0 for V infinity, if V infinity is greater than 0 with the direction taken this way, then that means this arrow sign is correct, right. So you have a positive quantity for arrow sign going towards the wave, which simply means that the burn gases behind the detonation wave will follow the detonation wave, right. So this implies that the burn gases behind the detonation wave follow the wave, right. But when you now try to say the burn gases are going to follow the wave, will they catch up with the wave? Will they go past the wave? That doesn't make sense. At least if they were to be able to go past the wave, then they will become reactants. but they are supposed to be products. So we better want them to actually kind of follow the wave rather faithfully, right. But what's going to happen in reality? So the question is, then if you now say V wave is equal to, so what do we have for the V wave? V wave is equal to u infinity plus V infinity, right. So if you now use this one here, you can find that V wave is basically V infinity plus u infinity, and we now find that both your u infinity and V infinity, the way they are defined in these two coordinate systems, both of them are positive, right. So this implies that V wave will obviously be greater than V infinity. And how did we define the V wave? V wave and the V infinity are in the same direction, right. Since V wave is greater than V infinity, it follows that the burn gases will never be able to catch up with the wave. The wave is going to travel faster than the burn gases, right. So this implies that the burn gases, although traveling in the same direction as the wave, can never catch up with the wave. Right. This is true even when you now have a weak detonation where the product gases are traveling at supersonic speeds. They travel at supersonic speeds that are still less than the supersonic speed at which the wave travels. Okay. Now when I say that, you got to be a little bit careful, because when you say supersonic or subsonic, it's based on the Mach number, and the Mach numbers, the way we are actually trying to deal with for the upstream Mach number and the downstream Mach number are relative to their respective temperatures, and in all these cases the upstream temperature is lower than the downstream temperature. Okay, so the downstream Mach number always would look like it can be lower. Okay, it does not mean that the velocities are lower, but what we are actually finding out in this is the velocity is lower than the wave velocity. Okay. okay, therefore it's going to it's not going to be able to catch up, it follows but it can't catch up. Alright. What happens when you now have a deflagration? So in the deflagration branch of the Hugoniot of the Hugoniot curve, we have 1 over rho infinity minus 1 over rho naught, right. So where is the 1 over rho infinity? 1 over rho infinity is on the right side when you get the solution for the lower branch when compared to 1 over rho naught, so that's actually greater than 0. Therefore if you now have 1 over rho infinity minus 1 over rho naught is greater than 0, then u infinity minus u naught equals m dot 1 over rho infinity minus 1 over rho naught is greater than 0, right. So u infinity is greater than u naught, that's no news. In the wave fixed coordinate system we know that the flow, the product flow is getting accelerated when compared to the reactants, but now we look at what the consequence is when you now have the lab fixed coordinate system. If you now say u infinity is greater than u naught and then go back here and look at what happens to v infinity, right. So v infinity is equal to u naught minus u infinity, that's coming out of the coordinate transformation regardless of the actual disparity between u infinity and v u naught, okay. And so this is for a general wave, this is for a general wave with still reactants, this is for a general wave. We have not said that it's a detonation at that point, it's only when you say greater than 0 we have invoked this, that's for a detonation, but it turns out to be this for a deflagration. If you now plug it in here you find that then v infinity equal to u naught minus u infinity, what do you get? U infinity minus u infinity is greater than u naught, therefore u naught minus u infinity is now going to be less than 0, that means v infinity is negative. V infinity being negative, the way the arrow is taken this way means that it's going to, the arrow is going to get flipped, right. So this implies that the burn gases, behind a deflagration wave flow away from the wave, in the opposite direction. So since the gases are going to go away from the wave, we don't have to worry about what their speed is relative to the wave speed, because they are never going to catch up, right. So let's not even do the extra thing that we did for the detonation, so we don't have to worry about whether they are going to catch up or not, they simply go away. So that means in reality what happens is, if you now have a deflagration that is propagating this way in still reactants, as soon as the reactants react you now have gases flow away in this direction if the wave is going like this, simply because they are getting accelerated and you had still reactants and you now have a pressure decrease and a density decrease. So it's an expansion that's going on with an acceleration, so the velocity that is accrued because of this tends to flow away from this region, right. That's what you get for a deflagration. Now we will see a couple of other thermodynamic properties. Yes.
The direction of surface changing, doesn't the relative velocity change?
No, this is basically based on the way we have actually accounted for these directions for the wave, and the in fact what I should say is we are also assuming a V0 like this. That's how you can get this coordinate transformation going. But of course we set V0 equal to 0 because we want to consider still reactance, and from where we get V wave is equal to U0. But I wanted to point out previously that V wave is assumed to be like this and U0 is assumed to be like this. That's how we got this transformation to be like this. And
but if my product flow is this way now,
yes,
and the wave is moving this way,
correct.
So when I put the relative velocity of the products, it would become VW plus whatever.
True. Then what happens is, see, why would you want to do that? So you would want to do, if you want to now factor in the relative velocity of the products relative to the wave, then you are going back to the wave fixed coordinate system, right? If you, what is meant by relative velocity? Relative to what? Relative to what? Yeah, relative to the wave. So if you now want to actually locate your velocities relative to the wave, you are going to your wave fixed coordinate system. Unless you are now trying to do, well, maybe not, maybe what you are saying is different from what I am saying, because when I am in a wave fixed coordinate system, I am actually counting my reactant velocity relative to the wave, okay. When I am in a lap fixed coordinate system, I am just letting the wave propagate in primarily still reactance, but it does not have to be still, okay. But if I am counting for a flow direction, I would count it like this. If the flow were actually approaching the wave like this in a wave in a lap fixed coordinate system, I would have to reckon V0 to be negative in the way I am doing this. What you are telling me is, once I actually find out what my actual V infinity is it possible for me to look at that velocity relative to the wave? That means we are now trying to look for making this still, if that's what I understand.
No. I'm saying like the equation what we have taken is for V infinity, it's VW minus U infinity.
V infinity is V what?
V infinity equation is VW minus U infinity.
Okay.
That's because I'm taking the direction like this.
Yes.
Of V infinity. But if I take the direction itself like this, then the relative velocity would become VW plus U infinity. So the equation there itself changes. So this process.
Okay. If you were to take your V infinity direction to be like this, you should get V infinity to be positive. Yeah. That's what you should expect. Yes. All right. Which would basically say the same thing. All right. So I mean you can work that out. Maybe what you do is you assume that V0 is going to be positive in this direction, V infinity is going to be positive in that direction. You should be able to show that if you were to actually make V0 equal to 0, right, then V infinity becomes negative for detonation wave and it's positive for deflagration wave. That will simply make this different. You would now write, you would now say that V0 is equal to U infinity minus VW, and V infinity is equal to U infinity minus VW. All right, that's how you will actually get these signs flipped. You should get the same thing, right? The question is all about being consistent about your these transformations based on the direction that you have assumed. Okay, so I guess that would be a little bit more straightforward maybe. If you were to assume the wave to go like this and still assume the reactants to go like this and the products to go like that, it's probably a lot straightforward to do the transformation, right? And all you have to do then is to show that V infinity is negative in the case of detonations and remains positive in the case of deflagrations, so that you have to show the opposite. Okay, maybe for the exam, right? So yeah, but it should be the same. All right, let's just go through a couple of quick thermodynamic properties other than what we have discussed so far before I come back to some realistic depictions of these waves and see what happens. So first thing I would like to point out is temperature temperature behind the waves, right. T infinity is greater than T naught always for Q greater than 0. What you can show is if the mean molecular weights of the reactants and products are assumed to be equal, that is 1 over sigma I equals 1 to n yi infinity divided by wi equals 1 over sigma I equals 1 to n yi naught divided by wi equal to w bar, then the temperature ratio T infinity by T naught equals P infinity by rho infinity divided by P naught divided by rho naught is greater than 1 for at Cj points. That is to say, you can show this at Cj points considering the simplifying assumption that the mean molecular weight of the reactant and product gases are equal, but that's just a mathematical exercise that you can go through. The second thing that I would like to point out is how the entropy varies. This is something that we have not talked about at all, but it's interesting to talk about entropy variation. Entropy variation along the Hugoniot right. So maybe we have these underlined to distinguish them. So it can be shown that, and it's not very difficult to show. I'll tell you how to show this. It can be shown that the entropy is a minimum at UCJ and maximum at LCJ. So that's basically again looking at the Cj points because they are more amenable to mathematical manipulation, given that you can match the slopes of the Rayleigh and the Hugoniot and get coordinates and so on. And then how do you show this? Okay, so I'm not going to show this, but you can show. Question is, how do you show this? Well, it's rather straightforward. What you have to do is you see that the Hugoniot curve is having P infinity on the vertical axis and 1 over rho infinity on the horizontal axis. So it's as if 1 over rho infinity is your independent variable and P infinity is your dependent variable, right? So what is suggested is you now try to express your entropy as a function of 1 over rho infinity as a independent variable still, and if you do that, and then of course the way you do this is you now assume a reversible hypothetical reversible reaction that can prevail between the end states, and then use like T infinity ds infinity equal to in the first law of thermodynamics, and so if you now do that, then you get a expression for entropy at the end state as a function of 1 over rho infinity, and use that expression to differentiate this entropy with respect to 1 over rho infinity at the Cj point. Note that I am not saying which Cj point, because whether it is maximum or minimum you are going to have the derivative equal to 0. So you should be able to show this. This is relatively easier when compared to the next step, which is you have to now show whether it is maximum or minimum, right. So what you will be able to show is with d squared s infinity divided by d 1 over rho infinity squared at ucj as greater than 0 and d squared s infinity divided by d 1 over rho infinity squared as less at LCJ as less than 0, right. So what is happening? What you will find is, I am just running out of space there, let me use this panel to depict what is going on. So if you now think about the way I said, that is, you have your 1 over rho infinity as your independent variable and you plot your s infinity as a dependent variable. Question is, how does it look like? Okay. Now this is good to do because the 1 over rho infinity is going to be the same in the Hugoniot as well as here, and we know what happens when you now have the 1 over rho infinity vary about its origin. The origin of the Hugoniot of course is 1 over rho naught, right, and then the 1 over rho infinity varies on either side. 1 over rho infinity increases in the deflagration, the lower branch, and 1 over infinity decreases in the upper branch for the detonation. But keep in mind that there is a region here which belongs to the first quadrant in the Hugoniot which is not covered, right. That means 1 over rho infinity goes from 1 over rho naught as the initial condition to a value, it jumps to a value that is where the Hugoniot cuts the x axis passing through the origin, right, because above this you have the first quadrant in the Hugoniot plot which is forbidden, and therefore you will find that you now have you will now have a curve that goes like that, and this is where your LCJ is, and then you have over here a curve that looks like this, which is where you now have your UCJ, right. So what we are basically saying is this is your region 1, this is region 2, this is region 3, this is region 4. So that means this is strong detonation. You have CJ detonation, this is weak detonation, we have weak deflagration, and of course we have CJ deflagration, then we have strong deflagration, right. Then let's think about what really happens in actual practice. Okay, what we have seen so far is something kind of trivial. We have assumed that we can treat whatever happens inside the wave as a black box and then just do balances across as if they just jump, but we need still to conserve mass, momentum, energy and so forth. And we have now come upon a lot of facts, like we should now be able to say that there are two kinds of waves that are completely apart. One goes as deflagration, subsonic, and another one is detonation and so on. And then we further looked at upstream and downstream conditions to point out that this is subsonic, that's supersonic, then you have strong, weak and all those things, right. But did we ever care about whether this really happens in reality? Okay, so realistic existence of these waves, of the different waves. The first thing is strong detonation. What you will find is strong detonations are not very easily observed. Okay, so seldom observed, and why so? Because it's a strong detonation. That means you have to have a large compression, and you have to make sure that the gases are decelerated down to subsonic speeds from a supersonically propagating wave, and you have to have large pressures there and maintained. Okay, so invariably the way detonations typically happen is if you now have a reactant gas in a confined region and they got ignited at the confined end, and you now have a wave that is beginning to propagate, you now have a confined region where the pressure can build up and stay, right. And once you can have this pressure build up, then you have a transition to detonation wave for what you're igniting, and you now have a detonation wave. But the moment the detonation wave begins to propagate, this space is vacated, right. So you can't really have the pressure hold on until you are able to actually have this confinement follow the wave, right. So this is what's called as a overdriven shock tube. So that means you have to have like a piston that runs along with the wave and keeps this confinement as it is in order to be able to preserve the very high pressure that's been obtained with the strong detonation. So it requires a special experimental arrangement, requires arrangement, what's called as overdriving the shock. Now CJ detonation on the other hand is always observed. That means whenever you have a detonation wave, there is a very high chance that it's always a CJ detonation, so always observed. In fact, in the experiment that I just discussed, if you don't have this overdriving, you have this detonation wave, right, and you started out with a strong detonation, let us say, because you had the confinement. And keep in mind what happens with a strong detonation wave. You now have a subsonic flow downstream, right, and you now have the pressure pulses that go and get reflected from this and begin to come back and hit the wave, because this is a subsonic flow and the pressure pulses can actually propagate faster than the product flow. Product is actually beginning to follow but at subsonic speeds, and it's not going to catch up, but it can allow for the waves to go, the pressure disturbances that are coming from the other side can actually pass through this because this is subsonic. Typically what then happens is you now have an expansion fan shouldn't say fan, you should say expansion wave, because we are basically looking one dimensional. So you now have this wave that go like this, and then there is a pressure buildup, and that also propagates, so you have an expansion region that's getting created, which can propagate through this and then go and try to weaken the wave. Alright, when that happens, progressively this wave is getting weakened down to Cj level, at which point the products are beginning to actually go at sonic speed, right. So once the products are going at sonic speed, the rarefaction wave that we talked about can never really go past them, right. They can go only at the speed of the products and not really reach the wave at all, and therefore you now stop at a Cj. So any strong detonation that has been created will always tend towards a Cj detonation pretty soon, and that's the reason why you will always find a Cj detonation unless you took this arrangement in order to preserve the strong detonation, right. So if you didn't do any such arrangement, you're going to be getting a Cj detonation. Third, weak detonation. Now this is also seldom observed. Here what happens is you're having the product gases travel at supersonic speeds while it is trying to follow the wave, and if you want to have supersonic speeds at which the products are traveling, you have to have chemical reactions that are happening in the wave happen so fast that they are able to actually produce products that can travel so fast. So this really means that you have to have chemical reactions that happen very fast, so you need to have very special mixtures that have extremely fast kinetics, so require special reactant mixtures that have extremely fast kinetics, fast when compared to the flow velocities of the products, so that you will get products. Otherwise you will still have reactions happening while you're still expecting products to happen. The products aren't happening because the reactions are taking taking time to happen. So that's about the detonations. Let's now see what happens to the deflagrations. Should talk about weak deflagration. Yeah. Sorry?
Weak detonations cannot form at all.
It's not really stopped by anything.
No, S is decreasing. Entropy is decreasing.
That's only for the that's only for the infinity condition.
At 1 by rho and naught I have S naught. Then whatever I get in this plot is below the value of
True, that's correct.
So it should not happen at all.
No, that's not true. Entropy is decreasing only for the system, because the system is being worked upon when you have a compression wave. What you really want to be looking for is the entropy for what's actually causing the work to be done as well. So it's the entropy of the universe that actually ultimately increases. It doesn't mean that if you have a particular system, entropy can't decrease. If you do work on a system, then entropy can decrease, but who is doing the work on the system will have a corresponding entropy increase, which will be greater than the entropy decrease that you find in the system. Because it's a compression, you will have a entropy decrease because work is being done on the system. Alright, so that's for another day. So according to what you say, none of this can happen, right? Well, you have to start from here. This is your starting point. So if you were somewhere here, you're still low, right? That's not true. So talking about weak weak deflagration always observed. Right. Here in fact if you now go back and look at your Hugoniot, and this is the origin, and let us say that is a CJ point, what we are talking about is somewhere that is like very close to the original value. That means if this is your P naught and this is your P infinity is just about little less than P naught. So most of your weak deflagration is happening very close to the original P naught and very far away from the LCJ. Okay, in other words you do not even go all the way somewhere here, you are very close there. That is mostly what happens. You are typically talking about open systems, and in open systems you have almost like a constant pressure process. It is only very close to the flame it is possible to have this acceleration and this expansion, therefore the pressure decreases a little bit, not a whole lot, right, and that is exactly what gives you a weak deflagration. Correspondingly if you are now thinking about a CJ deflagration, you simply have to say not observed. This is primarily coming from the numerics. That means if you just put the numbers in, you will find that you can't get the pressure to decrease significantly at all for the downstream case to be able to get down to a CJ level, right. And when you now finally talk about a strong deflagration, all you have to say is not possible, forbidden by second law. This is something that we have been talking about. So in reality in the CJ in the Hugoniot line we are pretty much confined to a region that is very close to where we started for the P naught, and you do not even go all the way to the CJ, can't really go past it at all in reality. Okay, so most of your deflagrations are extremely weak deflagrations, that is the way I would put it. So let us finally give some numbers on what these changes are like. So if you now look at detonation on the one hand, deflagration on the other hand, what are our M naughts? It is of the order of about 5 to 10. Here it is of the order of about 0.0001 to about 0.03. There are about 2 orders magnitude variation, but they are very small. U infinity over U naught, how does the deceleration or the acceleration happen? This is about 0.4 to 0.7 deceleration. Here it is about 4 to 6. You can work this out. If you assume constant pressure, you can work this out to be about 4 to 6 based on the temperature change. This is acceleration. P infinity over P naught. This is about, look at this number, 13 to 55 compression. This is about 0.98. There is about 98% pressure recovery there, so that is slight expansion. And this high pressure jump across the detonation wave is what causes all the damage in detonations. Okay, T infinity over T naught is about 8 to 21, that is heat addition. It is only slightly less over here, it is about 4 to 16, also heat addition. In both cases we are actually adding heat. And finally you look at rho infinity over rho naught, you have about 1.7 to 2.6, and over here it's about 0.06 to about 0.25. That's about it. So you get the picture on what do you get for these detonation or deflagration waves. In summary, you typically are looking at a CJ detonation or a weak deflagration when you're looking at these numbers, right?